Hey everybody, video 2 for day 4. We're going to be talking about polymorphic lists. So in the last video, we defined two different notions of list, uh, bool list and nat list, which were sort of specialized homogeneous lists. The nat list was lists containing only nat, bool list was lists containing only bools, and in both cases we had these constructors nil and cons. These were monomorphic in that any inductive we defined really only had one possible shape of thing that went in it. We're going to define a polymorphic list. Polymorphism like this is, or also called generics, maybe you've heard of that in a language you've used before, is a really important property. It means that you can define something like the skeleton of a data structure once, and then get to fill in the bits and bobs in the middle sort of as many times as you want with different things. It allows for code reuse, which is really important, and it also means that you're going to miss out on all of these typo bugs from you just like copying and pasting things over and over again. You can optimize something just once and get all the winnings. There are other bonuses too, in that there's only one thing to think about, which means it's sort of like the range of problems you could have is sort of narrower to just that thing. So, great. In front of us, we have now the polymorphic definition of lists. This is an argument type to the inductive, just like we've seen arguments to definitions and fixed points. And it's saying, hey, there's a type list, and list on its own is not a type. If you give me some other type, X, well then list X, that is a type. What's that type? Well, list X is an inductive type with two constructors, nil, and then cons, where cons takes one argument X of type X, and another argument L of type list X. So here we have an application. It looks like a function application, but what we're doing is we're applying something we thought was a type, list. List is what's called a type constructor. You give it another type, here X, and then you'll get a type constructor out. So list, if you like to think about it this way, is a function from types to types. That's what a type constructor is. So we can actually ask Coq to check that for us. What's the type of list? List is indeed something of type to type. Oh, sorry. So just in case you're wondering, this shows up twice because we wrote the colon here. If I get rid of it, we'll see it only once. That's because this form, with the colon after the type, right? This is what's called a type ascription or annotation. And here we're just asserting that like, hey, this term should have this type. Okay. So how do these constructors work? Well, if X is a parameter for some inductive type, then it's going to magically be a parameter to every constructor. So nil nat is, let me get rid of these just so we can see it once. Nil nat is of type list nat. It is the empty list that holds naturals. Right? It's not an empty list that can hold bools, it's an empty list that holds naturals. Okay, if we wanted to build a list with one element in it, holding nats, we could say cons nat 3 nil nat, and that'll be something of type list nat. Let me get rid of this. So cons nat 3 nil nat says, okay, I'm going to add 3 to the front of the empty nat list, and that'll give me another nat list, a list of nats. Excuse me, I should just say list nat, not nat list, which is the monomorphic type we defined above. Now, because of the polymorphism here, we can also say, hey, cons bool true, nil bool. Well, so nil bool, that's the empty list of booleans. And now we have a list containing one element, just true. Okay, Cox lists are homogeneous. That is to say, every element in any given list has to have the same type. Now, you could have two different lists. We see the two things we just checked back here. You can have two different lists that hold different things. That's all fine. But in any given list, everything in the list has to have the same type. The languages you've programmed in may or may not have that property. It really depends. Okay, so to demonstrate that, let's define a list, lnat. This is a list of nats. Now, if we try to cons a true Boolean on the front of that, we'll get a message saying, whoa, whoa, whoa. lnat has type listNat, while it is expected to have type listBool. Now that error message is right, but maybe confusing. Right? You and I may think of lnat as already existing and being a sort of fixed term of type listNat. So if there's a problem here, it's with this. And honestly, I think we're right. But from Cox's perspective, it looks at it and says, okay, well, cons, that means it needs a type. The type was bool. Okay, cool. If the type was bool here, that means that cons will need a bool as its first argument and a list bool as its second. So from Cox's perspective, as it's checking the types here to make sure everything is, well formed, it gets to the LNAT and says, whoa, 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 whoa. You wrote cons bool earlier here, and now you've given me a list of nat. This list of nats is wrong. And in a cosmic sense, are we right or is Cock right? It's hard to know. Like, what's the intention here? It's hard to know. This is just an exercise. What does that mean? But the thing I want to highlight is the type error message you get will always be correct, but it may not have your perspective, and it may not focus on the things that you want to focus on. Nevertheless, it is true your program has a problem if you get a type error. Right? There's no two ways about that. Now, the reason for the type error might not be what Cock thinks the reason is, and you have to keep that in the back of your head. Okay, let's look at some more types of the constructors. So in particular, what's the type of nil? Nil has the type for all x, list x, where x here is a type. That's interesting. We haven't seen this before. This for all is a universal quantifier saying, hey, nil's type says you give me some type x, and I'll give you back a list that could hold x's that will be empty. Let's look at cons's type. Okay, cons has a similar for all. It says you give me some type x. You give me an element of type x as my first argument. You give me a list of type x, list holding x's as my second, and I'll give you back a new longer list. Okay, so one thing that means in particular is that cons keeps you honest, right? The type that you give to cons, right, x of colon type here, has to be the type of the argument you give. So if we'll get a different failure on this example where I say cons nat and then I give a true. And here the type error that Cock gives is the right one. It says, okay, true is type bool, but it was expected to have nat. And that's really right? Like we said it was going to be a nat right here, and then it was true. Our bad. All right, one thing to note, in the HTML files, it'll be written in the mathematical way if you happen to be reading the book online at all, and that's upside down A, which is just pronounced for all. You can write it as one word like this, or with a space between. It's cool. Okay. Cool. So, lists. Let's define some functions on lists. Part of the promise of these polymorphic or generic data types was we'd get to define things once and for all. Let's look at length. So we saw two versions of length before for our monomorphic lists, one for nat lists and one for bool lists. Here we can write just one and it's going to work on lists of any type. How does it work? Well, it works like the ones we saw above. So let's just do a quick compare contrast. So here we have the nat list length. Here we have plain length. And the code is basically the same. There's one extra parameter to cons that we're ignoring. That's the type that we don't care about. But otherwise, everything looks pretty much the same. Length takes the parameter of the type that it's supposed to be working on, and then has to pass that on the recursive call. So there's a bit of extra work happening here in length. In a video or two, we'll see how to get rid of it. But otherwise, we're basically writing this sort of generic logic we saw that was specialized to the monomorphic data type once as generic polymorphic logic, and that's just going to work for all of our polymorphic lists. Great. So there's length. So let's test it on a couple of lists. Here we can check that the length of the list 120, that was our example nat list above, that should be 3. Beautiful. And then we can check that the length of the list true, true, false should also be 3. Fantastic. Okay, let's look at some partial applications just to get a sense of what's going on. So length nat specializes the length function to say, oh, I'm the function that takes a list of nats to nats. And that's exactly the type we had basically for the nat list version of length. And then length base says, oh, well, I'll take a list of DNA bases and return its length. But length on its own, it has another one of these for all types. Every time you have a polymorphic function which takes a type parameter, you're going to end up getting one of these for all types, where the type of the function kind of depends on the type you've quantified over. One more function, then we'll do a series of quizzes, and that'll be the video. Repeat. So repeat is a function that says, you give me a type x, you give me some element of type x, call it little x. What we're doing here is not perfect, right? This is a thing mathematicians love to do. Like the collection of things is a capital letter because collections are big. So like type here being a set of objects or whatever. And then an instance in that collection or an element of that collection, that's going to be a lowercase letter. This is, I think, really convenient for the person writing it and for the person reading it who knows what's going on. But if you don't know what's going on and you're trying to talk about it, you end up sounding like a lunatic. So for all x that are a type, little x of type big X, it's like you what? Little x, big X? Like if you've read classics, you're like Ajax Minor? What is he talking about? Uh, so if you like, it's often nice to say like, call that elem or something, right? And you could do this, right? Your variables don't have to be just one thing, right? Like that's great. So I'll go through this named elem. It's a thing you do need to be used to. Like I think experienced programmers do this because it saves them time. It's a mnemonic. But as you're learning, it can be really confusing to have things with the same letter, just different capitalizations. I think I can only assume, especially if you're not a native English speaker, not used to the Latin alphabet. Okay. Repeat. What does it do? You give me a type X. You give me an element of type X. Okay, so much clearer, right? Elem. And then you give me the number of times you like it repeated, and I'll give you a list with that many repeats. How does it work? Well, it's going to work recursively on count to build the list. So if the count is 0, just give the empty list with the appropriate type. If it's non-zero, well, okay, we're the successor of something. So cons one element onto, well, repeat for the rest of them. Okay, let's see how it works. So repeat here. This next one, this is a little tricky, right? Because it says nat42. Which one's the thing going to be repeated and which one is the number, is the count? You kind of have to remember the argument order. So think about it for a second. Look at the definition. Are we going to get 4 2s or 2 4s? 2 4s. Okay, we can repeat the Boolean false once. We can repeat it 10 times. But it's a lot of conses. Okay, we can also look at some partial applications and see just what types they have. Repeat bool false. Okay, that's just waiting for the number of repetitions you'll have, and then you'll get a list of bools out. Repeat bool. Okay, that's waiting for the number of elements, and then the number of times you'll do it, and then you'll get the list out. But we could have a list of days, whatever. Repeat on its own, yet another for all type. If there's a type parameter written up here, you're going to get a for all type. If the type parameter has parentheses. We'll learn a different way of writing it in a video soon. That means a lot of this will happen automatically. Okay. Tiny quiz, just a little understanding check. Let's go through each of them. Recall the types of cons and nil. And then we give them for you here. What is the type of cons bool true, cons nat 3, nil nat? Think about it. Pause the video. Okay, so how might you do this? One way you could do this is you could work it out from the bottom up. Say, okay, nil, that says for all x, is a type list x, so that means this will have type list nat. Con says for all x is a type, there's the type nat. We need a nat, okay, cool, that's right there. And then a list x, okay, but x was nat, this is a list nat, we're good. So this is a list nat. And then we'll check cons bool true. Okay, cons bool, okay, here's a bool. So the type x for this cons will be bool. Now we need a true. That's fine, that's a Boolean, and then this needs to be a list bool. Hey, wait a minute, this was the bad example Greenberg showed earlier. This is ill-typed. Another way to look at it is just be like, well, look, we saw this pattern, cons, type, element, cons, type, element, and throughout the list, if the types have to be the same, because coq lists are homogeneous. Okay, here's the definition of repeat. What is the type of repeat? Okay, so a good way to do this if you're not sure is to try to be mechanical. Ignore this part for now and be like, okay, well, this ought to be x, arrow nat, arrow list x. Okay, so that means this one's right out. So these are the ones in the gunning. It's probably not this one because we just defined it and the type seemed okay. So it's probably one of these. And then I said, well, wait a minute. If you have one of these type parameters, that means you're going to get a for all. So that rules out this one. So now we're down to these two. And now we'd say, well, wait a minute. Why? Never heard of her. So it's got to be 4, process of elimination wise. Concretely, what is the rule? Well, look, once you have something of type here, well, then later on, if you reference it, that means that's going to be a for all. And then the rest follows the usual rules for looking at the argument list and generating the arrows that you need. So the right answer here is 4. Okay, last one, and then we'll do some more videos about how you can get rid of some of this type annotation burden so that Coq can figure stuff out for you automatically. What is the type of repeat nat 1, 2? It's impossible for me to say the words 1, 2 without thinking of Lewis Carroll's poem, The Jabberwock, which if you have never heard, I recommend you go and look up. It's an absolute delight. It's hysterical. So what is the type here? Well, if you scroll up a bit, you'd be like, okay, repeat takes X as a type. Okay, that's going to be nat. Well, here we go, 4. This was the right answer. Let's just leave that highlighted. So, okay, the nat will be X, and so it'll be nat arrow, list nat. So that means it should be this, list nat. And we can check that one just to keep me honest. Whoop. Beautiful. Okay, cool. If you got these quizzes, great. I'm delighted. If not, but you sort of see where you went wrong, no worries. Maybe do some practice. Partnering up with somebody and sort of like one person with a Coq buffer open and the other not, and they sort of like you quiz each other is I think a great way to sort of make sure you can do the typing in your head. These are the sort of questions we might ask as sort of relatively easy ones on an exam, but also being able to do this in your head is critical for being able to program well, because you need to be able to look at code and know what the type of it is to be able to work with it effectively. If you felt really lost through these quizzes, no worries. Maybe watch the video again, maybe spend some time with Check, and maybe ask some questions on Zulip in office hours or mentor hours or in class. Okay, we got a bunch more videos here to talk about some other fancy typing stuff. It's going to get a little technical in the next few, so just kind of bear with me. And then we'll have some interesting programming that happens at the end. We'll learn about some other cool structures. All right, talk to you soon.